Good afternoon, everyone. And I just saw one chat. It says there is an AVV class at 14:25. I am aware. This meeting is recorded, so you can watch it at any time you want. That's why we have a YouTube channel as well. You can watch it at any time. Now, I'm just going to first of all ask, can everyone hear me? I should have asked that first of all. If you can hear me, just okay. Nathan, thank you. Mr. McCallum. Okay, now, if you don't have any questions, like I usually say, this is how this works. If you don't have any questions from your classes recently regarding electric fields and stuff like that, then I just do some problems. Okay, you don't have to stick around for the whole thing. You can stick around for half of it. Ideally, I would like you to stick around for the whole thing, but if you feel like after half of the time has elapsed, you are done, then you are free to leave. This is also recorded so you can watch it at your own leisure. Now, if you have any questions, now is your time to ask. Otherwise, you can just watch as I solve some of these problems, okay? Now, let's see. Now, these problems are on the PHYV side. Okay, we use them, but they are should be similar to FVV students. Okay, and I have a lot of students who ask, where can we find these problems? You don't need to go find them. They are here. I show them to you as I'm doing them. Okay. Let's just start with this question. Don't worry about the numbering of the questions. Worry about the questions themselves. Okay. The numbering is just so that we as demis can figure this out. Okay. Who does what so that we don't all do the same set of questions. Okay. So question number 9, okay, it's just to help us keep track. They say a 15, I wonder, it is not necessary for me to turn on my camera. Uh, so let's just, okay, but let me just turn it on anyway. Okay, where is it now? I'm just looking for the face camera. Hmm. The lights are off in here and it is dark outside, okay, in the streaming studio. Okay, so, uh, look, my face is not going to change the question, so I'll rather just keep it off. It's distracting. For me, there is. Okay. So let's look at question number 9. A 15 nanocoulomb point charge. Okay, so we have a 15 nanocoulomb point charge, and it's placed on the x-axis at x is equal to 1.5. So we have the x-axis. Okay. I always try to draw the situation, what is happening. So we have the x-axis, let's say that's 0. Then we place a positive 50 nanocoulomb point charge at x is equal to 1.5. Let's say this is 1.5, and we place this charge there. Okay? We place the charge there. It's a 15 nanocoulomb charge, a positive 15 nanocoulomb charge placed at 1.5 meters. Okay. Now, and a negative 20 nanocoulomb charge is placed on the y-axis. So a negative 20 nanocoulomb charge is placed on the y-axis at y is equal to 2 meters. Okay, at y is equal to 2 meters. Let me just scroll up. So you can see at y is equal to 2 meters. There we place a negative. Wait a minute, am I supposed to do? Okay, this is question 9, yes. Negative 20 Newton coulomb charge, nanocoulombs, Excuse me, I said Newton. And they ask us what is the magnitude and direction of the electric field at the origin. Okay, so they want the magnitude and direction of the electric field at this point here at the origin. Okay, now how do we calculate electric field? Okay, first of all, okay, let me just check. What is that? Hmm. Okay, so just okay. So we have this whole situation. Okay, we have a negative 20 nanocoulomb charge there at 2 meters on the y-axis and a 50 nanocoulomb, a positive 50 nanocoulomb charge at 1.5 meters on the y-axis. First of all, let's establish the directions of each of these electric fields. Let's say this positive charge. Okay, now we always assume that where we want the electric field, we put a test charge there, and usually the test charge is positive. Okay, so the test charge would be positive. Okay, so this positive charge here is going to push this positive charge, the test charge at the origin. Okay, that's how we determine which direction the charge is going to flow. Okay, at a certain point, the electric field, I mean, in which direction it's going to flow or point towards, because remember electric fields are vectors. Okay, so at the origin, assume that there is a test charge there. Okay, it would be positive. Now this positive charge here would push this positive charge at the origin towards the left. Okay, so let's say this is the test charge. Okay, this is the test charge at the origin. Okay, this 15 nanocoulomb charge is going to create an electric field that's pushing it towards the left. Okay, this is due to the 15 nanocoulomb charge. It's going to push or create an electric field towards the left. Meanwhile, the 20 nanocoulomb is going to, if this is a positive charge, negative 20 will pull it because a positive and a negative attract. So the negative charge will create an electric field that pulls the positive test charge upwards. Okay, negative 20 nanocoulomb. Okay, does everyone understand this? By show of a thumbs up if you get this concept. Okay, how do you determine which direction the charge will flow? The electric field. Okay, okay. Vuyo, Mr. Vuyo Matula. Okay, is your hand raised or do you understand? If you have a question, you can ask at any point. You can stop me at any point. I just see your hand raised. Okay, I assume there is nothing. Okay, now we have now these two vectors. Okay, so what are the values of these two vectors? We can actually work it out. Okay, so we have one electric field, component of one electric field is pointing that way and one that way. What is the values of this electric field? Okay, for the one pointing towards the left due to the 50 nanocoulomb charge, how do we calculate an electric field? Electric field is equal to K Q over R squared. That's how we calculate an electric field. Now, K is a constant, it's Coulomb's constant, 9 times 10 to the 9. I know some people tend to use, let me see if the sometimes certain colors don't show up. Let me just see. Okay, it does show up. Okay, but I need to just lower it a bit. And we have The charge itself in this case is 15 nanocoulombs, so 15 times 10 to the negative 9 divided by the distance between those two is 1.5 meters. Remember, this 50 nanocoulomb is 1.5 meters away from the origin. And that is squared. Do not forget to square it. If you don't square it, you get something what we call electric potential, and you are going to do it exactly after electric fields. You get a new formula. It's going to be exactly the same as this, except that that will now be uh, electric potential. And if you work this out, 9 minus 9 is 0. 9 times 15, that is 30, 30, 30. And then you divide it by 1.5 squared. That's 1.5 times 1.5. And you should get 60 nanocoulomb, newtons per coulomb. Okay, that is the unit for electric fields. Okay, this is the electric field due to the 15 nanocoulomb charge. That's the electric field. Now you can denote it whatever way you want. So far we have this electric field component, and it is 60 newtons per coulomb to the left. Now let's work out the one upwards, and that one is due to the negative 20 nanocoulomb charge. So let's work it out. Okay, electric field is equal to kq over r squared. So it's 9 times 10 to the 9, which is k. Okay, I'm going to run out of space here. Let's me rather write it here. Electric field is equal to kq over r squared, where k is 9 times 10 to the 9. Q is 20 nanocoulomb. Remember, you can technically add the negative signs here, but then you just need to know that they are only there for direction purposes only. Okay, to make it easier for yourself, or rather when I do these calculations, I never put the signs in the actual formula themselves. That's 9 negative 9 because it's 20 nano, because that negative just indicates or just helps me to define the direction. And it is 2 meters away if I'm not mistaken. 2 meters away. And there's another thing. Usually I never write, I just did though, I never write the units in. Okay? You can do that if you want. It depends on the lecturer of choice. The lecturer. Okay? So if you work that out, you have that this electric field pointing upwards due to that negative 20 nanocoulomb charge is just 45 newtons per coulomb. Okay, so here we have the electric fields at the origin. We have two of them, two components of this electric field. One is 45 newtons per coulomb upwards, and one is 60 newtons per coulomb towards the left. Okay, and there is the origin. Okay, we have these two vectors. Okay, let me see in the chat. Okay, someone said they can't see the screen. Just by a show of hands, can you see what I'm sharing? Can someone just... Okay, there is at least someone that can share, see what I'm sharing. Okay, okay, thank you guys. The last person who just raised their hand is Apelele Mkwanazi. That surname has been in the news a lot these days. Famous people are amongst us. Okay, Mas Apelele. Uh, sorry, I just noticed your surname. I did not mean to pick on you if that is okay with you. I do apologize if that was somehow not cool. Okay. Now we need to work out the net electric field. Okay. Now you can do this by various means. Uh, First of all, can someone take a guess as to how can we calculate? Can someone give me an idea of how I can calculate the net electric field from these two electric fields? Now, you need to know, guys, so all of you that are actually listening, that this part of the course is the easiest. Okay? I have told my FVV students last time, you can pass first semester with just your high school knowledge. You cannot do that with second semester because everything here is new. And this is where your calculus, soon your integrals, your knowledge of integrals is going to be tested. Okay, so can someone give me a hint as to how I can solve this? Okay, I want to find the net electric field. How can I solve this? Using what?
We can use Pythagoras.
Thank you, Nolutando. Yes, we can use Pythagoras' theorem. Okay, we want to find the net electric field. It's the one pointing in that direction. So let's go ahead and use Pythagoras' theorem. So E net, the net electric field, is going to be equal to the square root. And guys, vector decomposition and net vector solutions should be second nature to you by now. 45 and 60, doesn't matter which one comes first. And this now will give you 45 squared plus 60 squared. Uh, let's see, 60 squared. Let's just see quickly. 6 times 6 is 3000, so that's 3600. And 45 squared, that is 2025. And if you were to add them together, that's 5625. And the square root of 5625 is 75. Okay, so now we have found the net electric field, 75, but we do not have the direction. Okay, so now we know it is somewhere in this direction, and we know that its value is 75 newtons per coulomb, but we do not know exactly what is the, let me go back to this, okay, but we do not exactly know what is the angle. Okay, now remember we always measure an angle from the positive x-axis, but we can use our form of values. So this one would be 60, that one would be 45. So if we were to find out this angle theta, it would be the arctan or the inverse tan of, so theta is equal to the inverse tan of 45 over 60. And that, ladies and gentlemen, gives you an answer of, yeah, I don't know if I'm correct here. So it's, I think it's 36.87. We can just quickly check as well. So 45 divided by 60 is 0.75. So the arctan of 0.75. Let's just check that. I do have a calculator here for that exact purpose. Clear. There is these functions. So the inverse tangent of, where's the fractions? Mine. Okay, so point. I've already. It's 0.75. Close the bracket. 89. Seems inverse tangent of 0.75. 89. Now we have 89. Oh yeah, that's why it's negative. Some negative 9. Okay. So let's see. 89,23. Is this thing in degrees? Yes, it is. 23. Okay, now I have this angle. Okay, that is the angle of theta, which I don't think is that. It should not be that high. It should be more on the lower side. Let me see. There's something wrong here. Hang on a minute, guys. I'm thinking if my. I wonder. Oh, it's 75 here. Okay, it should be 0.75. Yeah, there it is. 36.86. I forgot to include the point. Okay, so 36. Okay, so we have the angle. That's how you can pick it up also, guys. I knew it must be wrong, that angle. It must be lower than 45 degrees. And how did I know that? Because the electric field pointing towards the left is 60, while the one pointing upwards is 45, meaning it must be more towards the lower end. Okay, so here we have the angle theta, but we never actually measure from the positive axis. Okay, so we want this angle. Okay, we want that angle. And if how do we get that? We subtract it from 180. Okay. So the actual angle that we want, let's call that beta. Beta is equal to 180 minus 36,86. 36,86, that's approximately 143 degrees. Not Celsius. 143 degrees. Okay, so that's approximately 143 degrees, the direction in which this thing is pointing. Okay, and that is a simple enough question. If you were to do by a raise of your by a thumbs up or whatever, if you were to get this question, let's say I did not do this question, you get it in a test or exam, would you be able to do it? Okay. Also, I made a slight miscalculation. I did not see that this thing is actually at, remember I assumed it's at positive 2. Okay. I assumed the charge was at positive 2 and that 1 was at 1.5 here. Okay. This, you call this thing, reading sign here, was in my way. This thing here that I'm actually clicking on now was in my way. So I didn't see the negative, but it's the exact same principle. The only thing that will change now, okay, if you were to take that as negative, okay, see there, this thing was in the way, so I just saw the 2 meters. But the only thing that would change, okay, is the charge is no longer at 2 meters, it is at negative 2. Okay? Meaning our end vectors will look like this. One will be still towards the left, but one will be downwards. Okay. Our net vector will still be the same. It will still be 75. And now if you were to work out theta, it would be 36 Still here. That's still the 36 comma whatever we had there. 36,8. It will still be that angle there. But now you add it, you count from the positive x-axis, so you just add 120, 180, excuse me. So if you were to add 180 plus 30, that is 216. Okay? So your answer would be 75 degrees in a direction 216,8. 75 newtons per coulomb. Final answer is still 75. That will not change. The numerical values are still the same. It's just the position is now shifted to negative 20. So it's 75 newtons per coulomb in the direction. It is no longer minus 36. It's adding 36. So it's 216,8. Let's see if one of our options is that. There we have 75 degrees at 216,87. We can check. And yes, it does say the correct answer is 75 newtons per coulomb at 260 degrees. Okay, so I hope everyone understood that problem. I did the first while I did it using a positive, in assuming that it was, or not assuming, taking it as being at positive 2 when it was in fact at negative 2. Nothing changes except the direction of the electric field. Okay, it's no longer pointing upwards, it's pointing downwards. That's the only thing that changes. And of course, if you do the same calculations and you find out that the angle is still theta is still the same value, which it should be, the net will still be the same, but now you need to add to 180 because it's in the third quadrant. Okay, now, and it's positive of course because tangent is positive in the fourth quadrant, in the third quadrant. Okay, let's see. Next question. Question number 10. Remember, this question numbers are for me and the other daemons. Okay, so they assume, let me just remove this thing. Okay, I hope everyone can see that. Let me see what you guys see. Okay, a positive 60 micro coulomb charge is positioned on the x-axis. Okay, at x is equal to 4 centimeters. Where should a negative 60 microcoulomb charge be placed to produce a net electric field of 0 at the origin? Let's look at this. Okay, we have, here's the origin, and then we have 4 centimeters away, we have a positive 60. 4 centimeters away, we have a positive 60 microcoulomb charge. Okay, where should we place a negative 60 microcoulomb charge to produce the electric field that is 0 at the origin? Okay, this is the distance between these two is 4 centimeters. Okay, can someone hazard a guess? Okay, where should I place a negative 60 microcoulomb charge so that the electric field at the origin is 0? Anyone? Can anyone take a guess or a stab at this problem? Where should I place a negative charge? A negative 60 microcoulomb.
I think to the left of the positive 60 microcoulomb. To the right, I mean.
Yes. Okay. Yes, you are correct. The second time, you should put it to the right. Okay. This is what's going to happen. Let's say that's the origin. Okay. Your positive 60 microcoulomb is going to create an electric field in this direction. Okay. Now you need to find out what is going to create an electric field. A 60 nano is going to create the same electric field, But where are you going to put it? You're going to put it on the left or the right. First of all, we need to figure it out. Are we going to put it on the left or the right? If we put it on the left, it's going to create an electric field in that same direction, which is what we don't want. We want an electric field in the opposite direction. We want an electric field in this direction. Okay. Now, what is going to create an electric field in that direction? Either a positive 60 on this side, or or we can create a negative 60 coulomb, which is what we've been given. We place it exactly on top of that charge. Okay, so if we were to place a negative directly on top of this charge, let's say, let me go red. If we were to place a negative 60 there, negative 60 microcoulomb, okay, positive 60 is going to push it this way, negative 60 is going to pull it that way with equal amounts in strength. Okay, so we are going to place a negative charge on the right, on the right, but at what distance? That is basically what we want. What distance are we going to place that charge? Okay, at what distance are we going to place that charge? Let's look at it.
Sorry, sir.
Yes, go ahead.
Uh, but according the way that I'm looking at this problem, since we already know that the net electric field it should be zero,
Is zero. Yes,
yeah, and we can calculate that charge that electric field of charge of 60 that we know is at a
yes, we
distance of
can.
4 meters of
Yes,
centimeters.
yes,
Then now, what about we calculate the electric field of 60, that of positive 60, then we get an electric field. Then we go to the formula of theorem of Pythagoras to get that net electric field. Then we know that a net electric field it is equal to U0. Then we have the electric charge of 60. Then instead of inserting the electric field, the actual electric field of negative 60, then we put a formula of electric field. Then we will say we have that K and Q, then divide by X all squared.
yes,
Then we equate it to zero. Then in that way we can calculate for the value of X, because that will be the one that we don't know.
yes, yes. I was just doing it theory wise, but yes, that is exactly mathematically how you will do it. For those of you guys who could not follow, this is what he said. Okay, we know the electric field. Uh, it was the student who spoke. Can you just speak so I can see your name right up, light up? The gentleman who just answered.
My name is Luaz Nwane. I don't know, maybe it's
Okay, yeah, I can see it. I need you to speak because I can see all of your names, but I don't know who spoke exactly. Okay, so Mr. Loazi. Okay, this is what Loazi said.
yes.
We know that these electric fields, that their sum should be equal to zero, right? This is what he said. And then we also know if their sum is zero, then we know that these electric fields, E1 and E2, must be equal, right? Everyone agree? They must be equal because their sum should be zero. They, I don't mean they should be equal exactly, but their numerical values should be equal. Okay? Because we must subtract one from the other and get zero. So numerically, they should be the same. The absolute values should be the same. Okay? Now, if the electric fields are exactly the same, we know that K times Q over R1, and we already know everything about R1, okay, should be equal to K times Q2, this is Q1, over R2. Now remember, R2 is the value that we want, okay, we want R2, but he just said instead of using R, he just suggested X, okay, because it is an unknown. We can do that, or you can just keep it as R2, or you can use X, okay. Then, so we know now that these two electric fields should be exactly equal, okay, but they should be pointing in opposite directions. Now let's substitute everything, all the values in. We know that KQ over R1, or let's rather use X, or I'm going to keep using R2. Okay, let's substitute everything we know. We know that K is 9 times 10 to the 9, and we know that Q is, in this case, it is 60 microcoulombs. It's positive 60 microcoulombs. Remember that? It's positive 60 microcoulombs. Oh, I don't actually need to write the positive. And then we know also, I forgot to write the square here, right? The distance is 4 centimeters. I prefer to always convert to meters. So 4 times 10 to the negative 2 meters. And it should be exactly equal. These two electric fields should be exactly equal. Okay? You can do this. Absolute value of that. And then we write here negative 60 microcoulombs multiplied, of course, by 9 times 10 to the 9. And we want this distance. We have been given that the other charge should be negative 60. And we know that the other one is also 60 microcoulombs. Okay. The only unknown that we have, and this is what Loazi was explaining, we then put it all in a formula like this, and we can calculate this value, the distance. How far should we place this value? Okay. And if you were to work it out, you will find that this cancels, that cancels, that cancels, that cancels. If you work it out, you will find that the distance that this charge should be placed at is 40 centimeters. The exact same distance that this charge is placed. Now what we need to find out is, are we placing it, where exactly are we placing it? Are we placing it on the right or on the left? Okay, well, the formula would have told you that already, the minuses and pluses. Now, we know that the positive 60 charge is going to create an electric field towards, if we place the positive 60 charge, it's already been placed 4 centimeters on this side, so it's going to create an electric field towards the left. Okay, so we need the other charge to create an electric field towards the right. Okay, now this negative 60, the only way that a negative 60 coulomb charge can create the electric field towards the right is when that negative 60 coulomb charge is also on the right. Okay, but what distance? We've already calculated the distance it should be is, it should be at negative 4. Also, rather, it should be at 4 centimeters. Meaning that this charge should be exactly placed on the other charge. Here is another thing. Okay, what happens? Can I ask you guys, what happens when you place two of the exact same charges in each other or on top of each other? Okay, can anyone answer that?
Can you please repeat the question?
What happens when you place two charges of equal value or equal charge, when you place them exactly on top of each other or in the exact same space? What happens?
The same charge.
Imagine this. Let me just look at my drawing here. What happens when I place a positive and a negative here? What's the overall charge there in that region?
Won't it give us an attractive force?
No, 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 no. Listen to my question. Let's say I have two equal charges, but one is positive and the other is negative, and I force them into the same space. What's going to happen to them? Let's say this is a positive charge. I have a proton and I have an electron, and they have the exact same charge, and I place them in some confined space. What will be the net charge? Yes, Mr. Mfigelelo is answered there. They will be neutral. You see, when you put a positive and a negative charge in the exact same space, they will cancel each other out. They will annihilate each other, meaning the net charge will be neutral. They will be zero. And if the net charge is zero, let's look at this. K if Q over R squared. If the net charge is zero, it means this whole thing is zero. The electric field everywhere will be zero. That's another way of looking at it. If you didn't understand, or this is a way of thinking, we already established that the negative 60 microcoulomb charge should be placed exactly on top of the other charge, or exactly where the positive charge is, so that they can create a net electric field of zero at the origin. Okay, we all uh, agree on that. Now, how do you test whether that will work? Okay, whether it will be zero. Okay, is by if you the net charge then will be zero at the net charge by these two charges will be zero. So that's another way of looking at it. Don't look in too much into it. But what you need to understand is Mr. Loazi and my train of thought. Okay, you need the only thing is you've already been given a charge. You just needed to find out where at what distance do I place this charge. Okay? And we've established that we need to place it at exactly 4 centimeters. But on which side, the left or the right? This is where the sign on the charge will tell you whether it's left or right. Okay? Because if it's positive, it will just add to the other one. But if it's negative, it will subtract from the other one. Does that make sense? Okay. I see Alizwa, Mr. Alizwa has already indicated he understood the assignment. Mr. Lwazi, was that more or less, or did I completely bungle your explanation? Mr. Azola, you have a question? Or are you
Yes, I have a question.
okay?
Like, I want to ask, like, in this case, like, the distance, the separation distance was the same only because the charges were the same.
Yes,
So if these charges went the same, like in magnitude or their size,
yes.
will it the distance between them or the net electric field where the point of interest be zero? Like, will the distance be also the same if the charges are not the same in magnitude?
No, 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 no. That is because the electric field is based on the charge itself. Okay, so if the charges change, the electric field is going to change. And if the electric field is going to change, that means they won't be zero at the origin. Okay, does that make sense? Okay. In this case, we were lucky because the charges were exactly the same. But if the charges were not the same and you needed it to be zero, this is what you do. If the charges were not the same, you will know that the electric field of one plus the electric field of the other should be equal to zero, right? This is what you know, okay? Because it should be zero at some point. Now, you know then the electric field of one should just be the negative of the electric field of two, okay? Then you can just work it out. K Q over R, and then K Q2 over R2, and you work it out for yourself, okay? You will be given this K, you know it's a constant. You would probably be given this 1Q and then 1R. And if the other Q is not the same as that one, but they do give it to you, you can just work out the R. Does that make sense? This is the general formula for this type of problem. Okay? You know that the sum of the electric fields must be zero. So you know that the electric field of one is just equal to the negative of the electric field of the other. And you also know the formula for electric field. You will be given all of the things except the one, either the distance or the charge that you need to work out, and that's it. Okay? Now I'm going to move on. I'm going actually much slower than I anticipated, but we need to pick up pace now. Okay, let's say a water droplet. This is question 11. Okay, this is where I'm going to ask one of you to, or see if you can pay attention, or if you're paying attention. A water droplet has a mass of 1 times 10 to the negative 12. Okay, it is located in the air. Okay, so this water droplet is floating in the air. So we have a water droplet floating in the air. Okay, near the ground during a stormy day. So it's just floating in the air, some random raindrop. Now, an atmospheric electric field. Okay, the atmosphere is creating an electric field. Okay, and this magnitude of this electric field is 6 times 10 to the 3 newtons per coulomb. And it points vertically downward. Okay, this electric field is pointing downward in the vicinity of the water droplet. Okay, now this droplet remains suspended at rest in the air. This droplet is just floating there. What is the sign and the electric charge on the droplet? First of all, if this droplet was neutral, it would not have floated. Because if you throw anything neutral inside an electric field, it's not going to be affected. Okay, an electric field only affects a charge, a net charge. Okay, so we have this droplet. Can someone tell me, this thing is suspended in the air. What two forces is affecting it? Okay, just anyone. If we have something suspended in the air, it's floating in the air. Two forces. There is one that is always there. It's always there. Whether you think about it or not, it's always there. Which one is that?
Weight.
The weight, yes. It's weight. The force of gravity is always there. Now, the force of gravity is counteracted by another force which should be exactly equal because it's floating at rest. It's not accelerating, so it's just floating in midair. So the other force must be equal to gravity. Which force is that? No, it cannot. It's not the air resistance, but that's a good thing. If it was accelerating, it would be the air resistance, but not in this case. Which other force is keeping it suspended? Remember, there is an electric field there. So what force is keeping it?
Electrostatic force.
Yes,
Electrostatic force.
yes. Thank you, Azolo. It's the electrostatic force. It's the other force that's keeping this thing suspended. So now we know there are two forces. Okay, that is keeping this droplet suspended. It's the electrostatic force and the force of gravity. And we can write that in mathematical form. It just says that electrostatic force is equal to the force of gravity in this case. That's why this thing is being suspended. Okay? But we know the force of gravity. How do we calculate the force of gravity? It's mass
We-
times gravitational
Yes.
acceleration, mg. How do we calculate electrostatic force?
We use the mass of an electron
Yes.
of a charge.
In this case, we want to work out what is the charge on this. But they do give us the mass of the water droplet.
Yes, it's a constant.
Yes. Remember now, how do we calculate electric force? Can you guys still remember this formula?
I think it's F is equal to Q multiplied by E, which is the electric field.
Yes, Alizwa, you are correct, completely correct. It's QE. That is how you get the electric force. Okay? Remember, we now have everything. Okay, we have the electric field. We have this thing's mass, the mass of this droplet, mass of d, and then we have gravitational acceleration. They want the charge on this droplet. Let's work it out. The charge on the droplet is then equal to its weight, mg, divided by the electric field E. Okay, let's work it out. The charge is equal to mg. Why do I write the Q? Mg divided by the electric field. The mass, what is the mass again? Let me look at it. Remember, I can't see everything. I have multiple pages open. You can see everything. What it is a 1 times 12. So 1 picokilogram. 1 times 10 to the negative 12. Is it kilograms? Kilograms, yes. We always use kilograms when using Newton's laws. And then gravitational acceleration 9,81. The electric field they gave us is 6 times 10 to the 3 Newton's Coulomb. And if you were to plug that into a calculator, you will get about approximately 1,6 times 10 to the negative 15 coulombs. Okay, that is what I got. Now, here's the problem I have with this question. Okay, remember all of these questions give you like an option of answers. Okay, uh, if the correct one is also they want to know, is this charge positive or negative? Okay, is this charge positive or negative?
Yeah, it should be negative.
Why do you say that?
I agree for the electrostatic force to be equivalent to the gravity. There must be in different directions, of
Yes.
which
Go on, go
it
on.
will, so the force will be the same as the negative direction of that one, which will change the sign of the charge. But we didn't include it here when we were computing the charge.
No, it will not necessarily come up in the calculations because we're just looking at the numerical values. But your argument, yes, is valid. The charge must be negative because remember, they tell us that this electric field points vertically downwards. Okay, this electric field is pointing downwards. Okay, now the only way that something, a charge will be able to, if the electric field itself is pointing downwards, it means that if you were to put a positive charge there, it would move downwards. Okay. Now, if you were to put a negative charge in there, it would move upwards, and that is what we want. Okay, we want upward movement because gravity is pulling it down. So the upward force is coming from the electric field, which must be moving it upwards. Does that make sense? Uh, Everyone understand that? They tell us that the electric force is downwards. Okay, the electric force is downwards. Okay, that means that anything positive will be pushed downwards. We know that electric fields directions are classified in terms of positive charges. So if we were to throw a positive
So
charge there, yeah, go ahead.
I want to ask, like, why didn't we include the sign for the electric field when we're computing here? Because
You can
this
do that.
formula,
Yes, you can do
but
that. But before you do that, you must then specify that upwards is positive. Do you mean like this? If I was to put a negative there,
yes, for electric field, because they didn't say the electric field has an absolute value.
yes, but they did tell us that it's moving downwards. But I could have chosen downwards as positive. In that case, you need to specify that you are choosing upwards as positive. Does that make sense to you? Remember, I can only make this negative if upwards is positive. Yes, okay, cool. So for instance, if Mr. Azola, if you were to do this problem, yes, you would be totally correct. You would get a negative there, but then you have to specify there that you chose that upwards is positive, meaning any downwards motion. So the electric field going downwards would be negative. Okay. So moving on to the next question. So we calculated where are we now? So we calculated the charge on this thing, okay, and it's 1.6 times 10 to the negative 15. Now I see here they tell us negative 1.6, but it is negative 14. Disregard that, it should be negative 15. Okay, I need to change that. Okay, let's look at this question number 12. Okay, there's one I'm not going to do. I think it's 13. There's something I need to fix that is horribly wrong there. Or I think I just need to do something. Check it out earlier. But let's look at number 12. Okay. Or I think it's 14. I don't know. Can't remember. Just 13. So this should be 12. 11. 12. This one. Oh, okay. I have it. So we have a charge. Okay, we have a charge. It's 50 microcoulombs. It is placed on the y-axis at y equal to 3 centimeters. And then we have a 77 microcoulomb charge. It's placed on the x-axis at x is equal to 4 centimeters. So let's draw what is happening. I always like to draw what is happening. That's the axis. So at y equal to 3 centimeters there, at 3 centimeters, we have a charge of 50 microcoulombs. And then at 4 centimeters, at the x-axis, at 4 centimeters, we have a charge of 77 microcoulombs. Now, if both charges are held fixed, okay, so these charges are in place, what is the magnitude of the initial acceleration of an electron with that mass, 9 times 1 to the 10 to the 9 times 10 to the negative 31, released from rest at the origin? So if we were to put an electron here at the origin, what would be its acceleration? Okay, how do we work that out? First of all, we need to calculate what? What do we need to calculate? If we're dealing with acceleration, of course, we need to calculate forces. Okay? So first of all, we need to calculate the forces at the origin. Right? The net force at the origin. Okay? So we must assume that we are putting this electron at the origin, or we are told we are putting this electron, this is the electron, it's at the origin. Okay? So first we need to calculate the force between this charge, the 50 microcoulomb charge, and the electron. So first we need to calculate, let me just do another color. First we need to calculate the force between these two, and then the force between these two, find the net force, and then from the net force we using Newton's second law, we can calculate the acceleration. Okay, so first let's work out the force between the 50 microcoulomb charge and the electron. Okay, so let's call this force 1 and let's call this force 2. So let's work out force 1. Force 1 is equal to K Q1 Q2 over R squared. You remember this from high school, grade 11. Now, K is 9 times 10 to the 9. I don't have enough space. 9 times 10 to the 9. Multiplied by, okay, let me just rather do it here. Force 1 is equal to K Q1. I keep wanting to make a G. Q1 Q2 over R squared. Then we have 9 times 10 to the 9. We have Q1 is equal to that charge of 50 microcoulombs And then Q2 is the charge of the electron itself, which we know is 1 times 10, 1.6 times 10 to the negative 19. Okay, and the distance between them is 3 centimeters, right? 3 times 10 to the negative 2 meters. So that way we have and then we need to square that so we can calculate the force between those two. Okay, so we know, first of all, we know that the electron is negative and we know that this charge, 50 microcoulomb, is positive, okay? So it's going to pull it upwards. The force between those two is going to be attractive. So the electron is going to be pulled upwards, okay? Remember, we have a 50 microcoulomb here and then we have the negative electron here. These two are going to attract each other, meaning the electron is going to be pulled upwards towards the 50 microcoulomb charge. It's going to pull the electron upwards. Okay? So if you were to work this out, 50 times 1,6, 19, negative 6, negative 25, negative 2 squared, that's negative 4, plus 4, that's 21. And you have that. Okay, so let's see. It is, oh, why do I do this to myself? I have the answer here. This, ladies and gentlemen, is the formula. Okay, it is 8 times 10 to the negative 11 newtons, and it is going upwards. I hope everyone understands why I said it's moving upwards, because that 50 microcoulomb is pulling it upwards. Okay, they are attractive because it's positive, the electron is negative. Now we need to work out the force F2 between the 77 microcoulomb, which is 4 centimeters away, and the electron. So 9 times 10 to the 9 times the 77 microcoulomb, 10 to the 6, and the charge on an electron is 1.6 times 10 to the negative 19. And the distance now is 4 times 10 to the negative 2 meters. And if you were to work that out, don't forget to square like I just did. If you work it out, you should get 6,692. If you have a question at any point, please stop me. 10 to the negative 11 newtons. And this one is to the right. Okay, it's to the right because it's pulling it towards the right. So this is what's happening to the electron. This is now from the electron's perspective. The 50 microcoulomb charge is pulling it upwards, and the 77 microcoulomb charge is pulling it towards the right. And we have these forces. Okay, we know that this force here is 8 times 10 to the negative 11, and we know that the one here down below is 6,92 times 10 to the negative 11. Okay, now we all know what we use in this case to find the net force there. We all know we use old Pythagoras. Okay, we use old Pythagoras. So the net force, this force here, F net, the net force, F net, can be calculated as the square root of those two forces squared and then their square root, the sum of those two squared forces. 92 times 10 to the negative 11 squared, and you find the square root of that, and eventually you get to the net force of 1,06 times 10 to the negative 10 newtons. This is the net force on this electron. Okay, now can I ask, we were asked to calculate the let me just show you there. We were asked to calculate the acceleration. Okay, how do we get acceleration from force? Okay, we use Newton's second law. F is equal to ma. Okay? We have the force and we have the mass. Okay? So acceleration is equal to it will be directly in that direction of the force. Okay, we can work out the direction as well, but they don't ask for that. They just ask the acceleration. So the force is 1,06, the net force. We can work out the direction if we want to. That's the newtons. And then the mass of an acceleration, or the mass of an electron, they've been giving it to us, or they gave it to us, 9,1 times 10 to the negative 31 kilos. Okay? And that gives us an acceleration of 1,16 times 10 to the 20 meters per second squared. And that is how fast this electron is accelerating inside this electric field. This is how fast this electron is accelerating in this electric field. Did everyone get that? It's a simple question. You first just need to find out the net force. Okay? Here, some are still with me. Okay, now number 13, like I said, I'm going to skip that one because there's something I want to check. Because none of these answers 13, no, there's 12. Remember, we just worked it out as 1,16. Let's just check. 1,16 times 10 to the 20 should be one of them. 1,2 is the closest. Let's check. Yep, it is 1,2. Okay. Then this one here, the vertices. I want to make sure about this value here. Okay. Let's go to question number 4. 4-point charges are at the corners of a square of side A as shown below. I'm going to show you guys now. What is the magnitude in terms of K, Q, and A? You guys need to be able to do this. And the direction of the net electric force on charge Q. You need to work out the direction of the net electric force. Okay, the net electric force. So, first of all, let's draw the situation. There's a positive, they're all positive, but they just have different values. Okay, imagine this is a square. You need to imagine very hard because I am a terrible artist. Okay, so there we have a square. Distance between them is A, and we have 2Q, Q, another 2Q, and then 3Q. They ask us to find what is the magnitude and direction of the net electric force. So we need to find force on the charge Q. Okay, so I'm going to keep the picture up, but I'm going to use it exactly as is shown there. Okay, so first of all, what's the electric force? First of all, they are all going to be pushing each other. Okay, so let's just determine, this is the one we want. In the upper right hand corner is Q. It's the one here. This is the one we want. We are looking at this one here. Okay, in the upper right hand corner. So we are looking at that charge Q. The one below it has 2Q, and then the other one next to it has 2Q, and the one directly diagonal across it is 3Q. So we need to first work out the forces between them. Okay, so let's see the force between our charge, which is Q, and the charge right next to it. Let's work out the force between, which is 2Q. Let's work out the force between the two of them. The force between, let's call this force 1. Okay, let's call it force 1. So force 1 is equal to, how do we calculate force? It's K Q1 Q2 over R squared. Okay. Now what is K? K is the same. It still stays a constant. What is Q1? It can be either of them. It doesn't matter. Let me do this. It's Q. Let's write Q. The other one is 2Q. This one is Q. The other one is 2Q. And the distance between them is A. So it's A squared. So if you were to write the answer, force 1 Also, in which direction is it? It's going to be pushing it. I'm going to show you now. Force 1, its effect on Q1 is it's going to push it that way. Okay? It's going to be pushing it towards the right. So it's K Q squared 2, and that's over A squared. Okay? That is force 1. Now, this is still Q. Let's work out the distance, the force between these two. Same distance, same charge, same charges. So its force is also going to be F is equal to 2 KQ squared over A squared. That's going to be force 2 because it's exactly the same as that one. The only thing is it's going to be pushing it upwards. Okay? So now we have two forces. Okay? On Q. Let's say this is Q. The force on the left hand side, upper left, is pushing it this way, while the force below it, or the charge below it, is pushing it upwards as well with the exact same force. Okay? Let's calculate the net force between these two. By the way, these forces are exactly the same, so the angle between them, the net force's direction, will be at 45 degrees. Does everyone agree with me? Okay, if two forces,
Yes.
okay, it will be exactly the same because they're going to be pulling it. One is not going to be slightly pulling it more or less, it's going to be exactly the same. Okay, so the force, so let's find out the net force. Okay, how do we find out the net force? We use old Pythagoras. So the net force between, remember we've only used two forces so far, so the net force is going to be the square root of, what's it again? It's 2k q squared over a squared, and you square that whole thing, plus, it's the exact same force for both of them, remember, a squared, and you square the whole thing. Now, if you were to work this out, okay, if you square everything on below, okay, if you square everything, you get 4k squared q to the power of 4 a4 plus 4k squared q squared a4. Okay, this is what you get. Now, if we were to add these two up, you will get 8k squared q4, or rather, yeah, that should be 4. K squared q4 a4. So it'll be 8k squared q4 a4, and it should be the square root of that if you were to add them up. This will be your net force due to only two charges. Okay, due to only two charges. Now, if we were to find the square root of this, okay, the square root of 8 is just 2 square root 2. The square root of k squared is just k. The square root of q4 is q2. The square root of a4 is just a2. And that, ladies and gentlemen, is two forces already done. And this is at an angle of 45 degrees to the normal. This is one force. Now, let's work out the last force. There is one that we did not include. Okay, we did not include one. It's the one here. There is one here. It is 3q. And this one was q. Let's work out the force between these two charges. But before we do that, we need to work out the distance between them. What is the distance between them? We know that this distance is a, and that is a. So this distance must be, according to Pythagoras, it must be, that distance is equal to a squared plus a squared and the square root of that. And that is equal to the square root of 2a. That is that distance. So let's work out the force between those two, Q and 3Q. So force is equal to K multiplied by 3Q multiplied by just Q over A squared. No, sorry. It's not A squared. It is the square root of 2 times A, and that's squared. If you work it out, you get 3K squared on top over 2A squared. That is that formula. Okay, so now we have a force. Also, this one in this direction is going to point exactly 45 degrees. So it will be also in 45 degrees. Okay, so we can add it exactly to that one. So the final net force is equal to, let me just write it here, F net is then equal to the one we had before, which I think, if I can remember correctly, I should have written these things down, or it was 2 square root 2, if I remember, K Q squared over A squared plus the other force that we just calculated. I believe it was 3K Q squared over A squared. Okay, or was there something missing? Oh, there's a 2. There's a 2 there. Now, if you do this is then basic algebra. Okay, if you do this, it's 2A squared. This becomes then 4V squared K Q squared plus 3KQ squared. That's the formula. Right? Then, of course, you can take out the common factors. If you take out the common factors for both of them, is then 2A, of course, 2A squared. That is KQ squared. And you're left with 4. Okay, if you have a question, you can ask while I'm writing.
Like it is, shouldn't the denominator, like the LCD, be 2a to the exponent 4?
No. In this case, you just look for a common factor. You
Or a
can
common
use,
factor?
yes, you can use 4, but then you'll have to have A squared on top as well.
Oh, okay.
So this is what we finally end up with. This is the a net force on that charge. By the way, you need to take very cognizant. We used to be lectured by Professor, and he loved this type of problems. Okay, he hated anything that has numbers in it. So this should be the answer: KQ squared over 2A2. Let's see if one of our options is that. If we are given an option there. So it should be KQ squared 2A 3 plus 4. That is C. And it's 45 degrees above the x-axis. Let's check if it is indeed C. Yes, it says the correct answer is that one which we just worked out. Now, our second to last problem. We are nearly there. This one is quite easy. A particle, that's question 15. A particle whose mass is 4 grams and charge is 80 microcoulombs moves in a region of space where the electric field is uniform and is given by Ex is equal to negative 2.5. So in the x direction, negative 2.5, in the y direction, 0, and in the z direction, 0. So it is moving only in the x direction. Okay, so this electric field is moving in the x direction. If the velocity of the particle at time t naught is given by 80 meters per second, and its vertical and horizontal z components and y components is 0, what is the speed of the particle at 2 seconds? Okay, so there is an easy way to do this. Okay. First of all, we are only interested, everything else is zero, so we can just say in the x direction. So the force in the x direction, let's calculate. We are working with, we want velocities, but we do have forces. Okay, so we can calculate the force. So the force in the x direction is equal to the charge multiplied by the electric field in the x direction. Okay, that will give you the force in the x direction. So the charge on this particle is 80 microcoulombs. So it's 80 times 10 to the negative 3. And then the electric field in the x direction is giving us negative 2.5 in the x direction. Okay? If you work that out, or if you multiply them, whatever we choose to say it, negative zero point 0.2 newtons. Okay, so in the x direction, the force is negative zero point 0.2 newtons. So in the to the left, basically. Okay, so we have the force in the x direction. Then they tell us that at time naught, the acceleration, we can then work out the acceleration, okay, in the x direction. We can work out the acceleration in the x direction. We have the force. We then know the acceleration is equal to the force in the x direction divided. Remember the force, okay, let me just put it here. The force in the z direction is equal to the force in the y direction, which is equal to 0 because there is no electric field in those directions, so there's no force. So the force in the x direction divided by the mass should give me the acceleration in the x direction, right? So the force is negative zero point 0.2 and the mass we've been given is 4 grams, so it's 4 times 10 to the negative 3 kilograms, and that gives us an acceleration of negative 50 meters per second squared. So negative 50 meters per second squared is the acceleration in the x direction. And one important thing you should note that the force and the acceleration are both negative, meaning they are in the same direction. If you have a question, you can ask.
Sorry, sir, isn't micro negative times 10 to the negative 6?
Yeah, but that's not micro, that's milli. Sorry, I said micro. That's my mistake. It's milli, it should be milli. It's M.
Oh,
Micro
okay.
has that sign mu. Oh, it's milli. Okay, so now we have both the force and the acceleration in the x direction. What do they want? They want the velocity of the particle at t is equal to 2 seconds. Okay, now you need to go and look at your formulas from mechanics. Okay, since everything else in x and y is 0, we know that the velocity in the x direction is equal to the initial velocity in the x direction plus the acceleration in the x direction times the time. We have the acceleration in the x direction and we have been given the time 2 seconds. We have the initial velocity of 80 meters per second. It's been given there that Vx initially is 80 meters per second. And we can find the final Vx. Okay, so let's plug it in. Initial velocity 80 meters per second plus the acceleration we just calculated it to be negative 50 meters per second squared multiplied by the time we want it after 2 seconds. That is not 25, that is 2 seconds. And if we work it out, we get that this is actually, that's negative 100, so it's 80 minus 100, so it's a negative 20 meters per second. So after 2 seconds, the speed is going to be negative 20 meters per second in the x direction. But we know that Vx is equal V Vy is equal to Vz, which is also 0. Okay? So the final speed then is basically just 20 meters per second, and it's only in the x direction. Okay, then the last question, question number 16. Quite an easy one. A positive electric charge, a positively charged particle, sorry, accelerates from east to west. So it's going towards the left, my left, in a uniform electric field. What is the direction and the value of the electric field if the particle has a charge Q equal to 3 microcoulomb, a mass of 3 milligrams, or milligrams, yes, and if the value of its acceleration is 0.03 meters per second? Select the closest answer from below. They give us, we need to select the closest. Okay, we know that force is equal to mass times acceleration. Okay? We know that the electric force can be equal to Q times E, and that's equal to mass times acceleration. Now we have been given that this particle has a charge. Where do we want? First of all, what do we want? Okay. We have the acceleration. We want the electric field. So the electric field is equal to the mass times the acceleration over the charge. So the electric field equal to mass times acceleration over charge. The mass in this case is 3 milligrams. 3 times 10 to the negative 3. It's 3 milligrams. So it's 3 times 10 to the negative 6 kilograms. 3 times 10 to the negative 6 kilograms, because we need to work in kilograms. Okay? And then the charge is 3 times 10 to the 6 micrograms. Or 3 micrograms, or 3 times 10 to the 6 coulombs. Coulombs, not grams. Coulombs. And then finally, the acceleration A is 0.003. And if we work that out, we find the answer to be the electric field to be 0.03 newtons per coulomb. Wait, did I make a mistake? Oh yeah, that is the mass. That is plus, that's 3 divided by that, that's 0.03 newtons per coulomb. Okay? And then they asked us to find the answer that's closest to 0.03. And that the answer, by the way, the positive charge particle accelerates from east to west. Okay? And they want the electric field. It's positive, so it's going to be in the same direction as the electric field, so it's going to be from east to west. So the answer should be in the westerly direction, and the closest one to 0.03 is 0.01. They asked us to get the closest one. Let's check it. Let me see. Yep, the correct answer is 0.01. It's the closest one. The closest is 0.03. That is all the time we have for today. Thank you for listening. All the best with all of your endeavors. I'm going to, if there are any questions, please ask now, because I'm going to switch it off. Uh, if you have any questions, please ask now before I switch off. Thank you, guys. Thank you there, Mr. Alizwa and Loazi, Aluver, Zola. Thank you guys for listening. I'm going to switch it off now. If you have any questions, please ask. I'm going to stop sharing. Enjoy the rest of your day. Bye bye.